Okay, so hello everyone. My name is Kunal and I'm your physics tutor. And we are actually doing chapter Oscillations, and today is our lecture number 4. So let me write it here, in which we are actually dealing with simple harmonic motion. So let me recap the thing कि हमने previous class में क्या क्या चीजें cover करी थी. So we are actually covering the things like phase and all. हमने previous class में phase पे बात करी थी, जहाँ पे हमने दो चीजों पर बात करी थी. Like x is equal to something we can write a sine del. So this is our actually phase in which the del is equal to omega t plus phi, where this phi is known as initial phase. I hope this is all clear to all of you. And the next thing, we actually derive a formula for change in phase difference with change in time. So we derive the formula like del is equal to 2 pi by t into we're actually write it here like change in time. So this is the actually formula that we derived in previous class. So now in today's class, we are going to discuss about something new topic, which is termed as phasor diagram. So let me start our today's topic. It's termed as phasor diagram. Okay. So actually the phasor diagram is termed as, let me write it here, what it is actually. So it is actually the conversion of simple harmonic motion into uniform circular motion. Uniform circular motion with same omega as simple harmonic motion. As we read about the like omega is like angular frequency, and omega is actually rotational speed as well, right? So हमें क्या करनी है कि जो सिंपल हार्मोनिक मोशंस है उसको हमें कन्वर्ट करनी है यूनिफॉर्म सर्कुलर मोशन में with taking same omega, which will be taken as angular frequency in simple harmonic motion. So let me draw it here so you can, let me write it here. So it will be drawn as something like that. There is our minus a and there is our plus a, right? I think it's big, but okay, nothing to worry about. Okay, so this is our actually circle, and I have to draw in such a manner with something termed as like this. Okay, so this is our actually mean position, and this is our plus a, this is our minus a, right? And okay, and one more thing, we are taking phase here from vertical. Okay, so this is our let me called as, this is our phi initial phase difference. That means our initially our particle is at that position. If I'm telling that position, it will be termed as like something like that. Something x is equal to x naught. Okay. And phi plus omega t is our, so our equation will be termed as x is equal to, there will be amplitude A sine omega t plus phi naught. The thing that you have to keep in mind that we are taking the initial phase from vertical, right? And in this, the coordinate system is something different. This is our first quadrant, this is our second quadrant, this is our third quadrant, this is our fourth quadrant. We are actually considering in this way. In normal, we are considering first, second, third, and fourth quadrant. But when we actually when we do the conversion of simple harmonic motion into uniform circular motion, that means we are representing the simple harmonic motion in uniform circular motion. So we have to move in that, move in actually clockwise way. Okay, so 1, 2, 3, 4. This is our actually coordinate system. So this thing that you have to note it. So let me write it here, some noted point that you have to keep in mind. The first point is phase is taken from vertical. phase is taken from vertical. Second thing that you have to keep in mind is projection of displacement of particle on horizontal line represent as a channel. Okay. And basically जो इसकी जो मैं प्रोजेक्शन ले रहा हूँ ना यहाँ पे ये on horizontal line, so this line will be represented as simple harmonic motion, and same thing will be represented in form of circular motion. Okay, so you have to keep this thing in mind. So this is basically our phasor diagram and all. Now we are actually moving to our next topic, which is actually मैंने पहले भी कहा था कि हमें मेजरली इस चैप्टर में इसी पे बात करना है, which is actually termed as time period and frequencies. So let me start it here. So you can draw it here as well. You can do practice as well. कि जो भी है उसका बस projection ले लेनी होती है. So it's actually weights, nothing. Just convert the SHM into circular motion is termed as phasor diagram. So let's start our today's new topic, which is termed as time period of simple harmonic motion. Time period and frequency of simple harmonic motions, obviously linear. So actually there is two methods to calculate the time period and the frequency. The first method is actually we are first method and the second method. The first method is actually force method. We are actually try to find the time period using dynamics, and the second thing is actually energy method. So we are actually gonna read the both method, but first we are proceeding to the force method. So let me here write it here. Force method. So what is its procedure? Let me write it as the, so in step one, let me write it as step one so you can connect it with. So first you have to identify its mean position. जो भी ऑब्जेक्ट है उसकी सबसे पहले अपने मीन पोजीशन को let me write it here in a clear manner so you can understand. Wait, okay, so first identify mean position and write equilibrium equation. In second step, what you have to do, just you have to write the dynamics at displaced position. This is actually important. Dynamics of particle at displaced position. यहाँ पे आपने डिस्प्लेस करा, वहां पे क्या लग रही है नहीं लग रही वो आपको देखना है. And write the restoring force. Next, what you have to do, step 3, convert the restoring force in form of Fr is equal to minus of K of X. Taking help of, obviously, let me write it here, taking help of equilibrium equations or any approximation as well, wherever it uses. So you just use our approximation, right? And step 4, you can write like Fr is equal to, if you termed as minus of Kx, so your time period is 2 pi root under m by k. How I'm writing this? Because look at it, our omega square is actually k by m. So our omega is nothing but root under k by m. And time period is nothing but 2 pi by omega. So it will be termed as 2 pi root under m by k, right? So, okay, this is the thing that you have to repeat. First, you have to identify the mean position of the particle, and then you have to write the equilibrium equations, and then you have to find the understand the dynamics at displaced position, write its equations as well, And then you have to convert the restoring force into the form of minus of kx. And how can you do so? So you have to use your equilibrium equation to convert it into f r is equal to minus kx form. And then our time period, we can directly write it as 2 pi root under m by k. Okay, so let's start with some basic example. So let me write it here. Let me take our first system, which is actually termed as spring block system. Spring block system. Let me write it here. There is some m mass, and this is actually our smooth surface. So, and it has stiffness constant K, and you have given at mean position, spring is relaxed. So you have to calculate its time period. Find time period. Basically, if you calculated the time period of frequency will be easy, it's just the 1 by t. Find time period of the given system. So how can you do so? So first we have to write the equations at equilibrium position. So first we have to identify the equilibrium positions, right? So here our actually equilibrium position is this, because here the net force is zero, right? How can I say so? So in x direction, this is our x-axis, this is our y-axis. So in x direction, we have actually no force, right? Like net force is equal to zero. F net in x direction is zero, right? Because in this direction, the particle is rest. Initially at rest, we are talking about initially, right? So there is no force. What about in y direction? So yeah, in y direction, there is two force. Let me write it here. There is mg force, which is acting vertically downward, and the normal force which applied by this smooth surface on the mass m. So in y direction, also F net in y direction is zero, because normal is actually equal to mg. So net force on the system is zero. F in y direction, you know. And the next thing what we have to do here is we have to write the equation at displaced position. So let me write it here, displaced positions. Okay. So let me draw it here again. We are actually, okay. So this is our M. This is our smooth surface. And let me call here, there is our something, our mean positions. So from mean position, there is a displacement by x. This is in positive direction, right? There is we called as x is equal to zero. So right now there is some acting force in x direction. So in x direction, if we are taking about, we have actually a force of kx in this direction, right? And in y direction, we have, so here the f net is equal to actually minus of kx. And in y directions, again, there will be simple mz downward and normal upward. So f net in y direction is still zero, right? So here the time period we can directly send as 2 pi root under m by k, because it's directly come into this form, which we are talking about in this system, right? So here the time period is, we can say 2 pi root under m by k. If we are like, you do the same thing, right? Omega square is equal to k by m. So omega is equal to root under k by m, and our time period is nothing but 2 pi by omega. So we can write it as 2 pi root under m by k. I hope this will be clear and understand, right? So here what we can use, we use here x as elongation in a spring, or we can also termed as displacement of particle from mean position. Displacement of particle from mean position. And yk is our spring constant. One thing if here is given, assume mass is actually 1 kilogram and K value is something like 100 of pi square Newton per meter. So you have to find time period and frequency. So how can you do so? Okay. So what I have to do it here, we actually get a formula like time period is equal to 2 pi root under m by k. So we have to just put in that equations, right? So 2 pi, our actually mass is given, which is actually 1 kg, 1 kg, and k value is actually 100 of pi square. So our 2 pi by 10 pi, 1 by 5 second is our time period, right? And the next thing we have to find the frequency. So we all know that frequency is equal to 1 by time period. So it will be equal to 5 hertz. That means 5 oscillations per second is actually going on. So this is the thing. Okay. Now let's take the another case in which actually force is acting, same system, but we actually just change something here. Uh, in previous problem, we are not considering any kind of force initially, but at this time we are actually considering some force here. Let me write it here. This is actually our smooth surface. Okay. And this is our actually mass M, and this is actually relaxed. And initially there is some force acting on the system F naught actually, and this is actually constant. And this is actually x is equal to 0. And this is actually at rest initially. So you have to find the time period. Look at here. Here, force is acting on the system. So we have to identify the mean position. So is x is equal to 0 its mean position? Obviously not. Why? Because there's force is not 0. Mean position where actually force is 0. So initially, in x direction, what we have to do, we have a force F naught in this direction. Let me write it here. F naught in this direction and something kx not in this direction. So if I have to find the mean position, so it will be actually equal to F naught by k. This is our actually mean position, whatever we get it from here, right? That means F naught is equal to kx naught basically. Now, if I displace the system by some x, let us assume this is our actually mean position, which is at x naught, and we are something displace it from here to here by x. And still there is acting of some force, which is actually F naught. So here, at displaced position, at displaced position, in y direction, still there is only mg and normal force, so we are not considering it. In y direction, net force is always 0, right? Because uh, force of actually gravity, force of gravity is anti-parallel to normal force, right? So its vector sum will be 0, so it will be net force on the system in y direction is 0. Now, what I'm trying to do it here is at a displaced position. Okay. So at displaced position, we have actually two kind of force. The one force is still acting on this direction, which is actually F naught, and which is actually balanced by kx naught. Okay. And there in this direction, our spring force is acting, which is actually x plus x. So if I'm talking about the restoring force, so it will be something equal to F naught minus kx plus x naught. And we all know that F naught is equal to kx naught. So let me write it here, kx naught minus kx and minus of kx naught. It will get cancelled. So Fr is again in this form. So if I get in this form, our time period is equal to 2 pi root under m by k. Okay, again, irrespective of that, initially there is some force acting on the system, which is actually constant force. It's again time period is same as when there is no initially when there is no basically acting of any kind of force, right? Initially here in x direction कोई भी फोर्स नहीं लग रही है, और यहाँ पे जब फोर्स लग भी रही है ना तब भी कुछ फर्क नहीं हो रहा. The time period will be remain same and its value is actually equal to 2 pi root under m by k. So यहाँ पे एक नोट करने वाली बात ये बस है कि in above question time period is same but mean position is shifted by x naught, which is actually is equal to f naught by k, and amplitude a is equal to x. So this is the thing that you have to keep in mind. Okay, and just in this case, our mean position is at x is equal to 0. But in when force is acting on the system initially, so our just time period will be remain same, and just there is a shift in mean position, which is actually by f naught by k, and the amplitude is x naught, and the rest of the thing is remain same. I hope it will be clear to all of you. So what we can conclude here is, let me write it here, the conclusion, which is actually important for single block system, for single spring block system, time period is always is equal to 2 pi root under m by k. Is it clear? It is actually. ठीक है, ये काफी इंपॉर्टेंट है कि फॉर सिंगल मास सिंगल ब्लॉक सिस्टम के लिए टाइम पीरियड इज एक्चुअली ऑलवेज इज इक्वल टू 2 pi root under m by k. चाहे कैसा भी सिस्टम दिया रहे, you can directly write it here. A time period is equal to 2 pi root under m by k. So let me write it here. Let me take it as a question. So there is a one spring and there is a big mass actually, which has mass capital M, and there is a two small block is kept here, and just you have to find the time period, right? And second question, there is a wedge which kept at angle theta, and there is a block of mass M, and there is a one spring. This is actually smooth, obviously. You have to find the time period. Okay, so what you have to do it here? Look at it. There is only one spring, right? So our time period is simply is equal to time period is equal to 2 pi root under. From above conclusion that we are get from above two problems is equal to 2 pi root under m by k. Here m is total mass is m plus 2m. So here we can write it as m plus 2m by, and here since the time period is by 2 pi root under m by k, and here mass is small m, so small m by k. So I hope it will be clear to all of you. Okay. Now discuss some more problem based on it. So it will be standing to all of you, right? Okay, so let me take the third questions. Okay, so it will be something like this form. यहाँ पे इसको हिंज कर दी गई है, and there is a mass m, and there is another mass of m, and somehow it will be balanced for just for second, and you have to find its time period, right? So for all case it will be remain same, no changes here, so it will be remain like 2 pi root under 2m by k. So we can write 2 root 2 pi root under m by k. I hope this thing will be clear to all of you. Okay, so now, now in next class, we are going to discuss some things like series and parallel combinations of spring. Okay, so actually we derived some formula. Actually, we derived some formula in it. That's all for today's. Thank you.